Alright, so let's take a look at the homework, 4.1. A theater wants to take in at least $2,000 for the matinee. Children's tickets cost $5 each, and adult tickets cost $10 each. The theater can seat up to 350 people. Find 5 combinations of children and adult tickets that will make the $2,000 goal. Okay, so we've got the adult tickets and the children tickets. So we want to know how many adults and how many children will get us to that $2,000 goal. And it has to fit within the 350 people. Okay, so let's say if we went with just adults. Okay, so if we went with just adults, an adult ticket is $10. So to get to 2,000, we would have to sell 2,000 divided by 10, 200 adults. Okay, can we seat that many adults? Yeah, you betcha we can. So there's one option. Okay, what if we wanted to do all children? So 2,000 divided by the $5 would be 400 children. So we couldn't do that, so that one wouldn't work, would it? Okay, because that would be too many children. And if we went to 350 children, 350 times 5 is only 1,750. Okay, we could probably, we want at least 2,000. So really, we could go 350 adults and 0 children as well. Okay, but let's try some others that aren't just adults. Okay, so let's say we wanted to do 100 children. Well, let's do, so 350, let's do 200 children, and that would be 150 adults. Okay, so we could do that. Would that get us more than 2,000? So 150 times 10 would be 1,500. 200 times 5 would be 1,000. So yeah, definitely, that'd be 2,500. So that'd be another good one we could do. Okay, what about if we flipped it and did 200 adults and 150 children? Okay, so the 200 adults would get us definitely 2,000. Adding the 150 kids would get us another 750, so that would definitely be enough. Okay, what if we tried to split it almost down the middle? So let's say we went with 175 of each. Okay, would that be enough? Well, 175 times 5 would just give us 875. 175 times 10 would be 1,750, plus 875 would definitely be more than 2,000, so any of those options would work, and a bunch more. Okay, the Utah Jazz scored 102 points in a recent game. The team scored some 3-point shots, 2-point shots, and many free throws worth 1 point each. Find combinations of baskets that would add up to 102 points. Okay, so this time we've got 3, right? We've got free throws, regular shots, 3-pointer shots. Okay, so and those are the different shots. So we want to decide, okay, what are some combinations that would add up to 102? Okay, well, let's say we made 10 3-pointers. Okay, so if I go 102, well, 3 times 10 would be 30, right? So 102 minus 30. So we made 10 3-point shots. Okay, we have 72 points left over. Okay, so if we divide it by 2 and we never had any free throws, that would be 36 2-point shots and 0 free throws. Okay, there's one option we could use. Okay, what if we took 10 free throws? Okay, so we'd go 102 minus 10, which would give us 92, and then maybe say we've got 5 3-pointers. So 5 times 3 would be 15, so minus 15 would give me 77. So I'd have to add another 3-point, right? Or another free throw. So 76 divided by 2 would mean we would have made 38 2-point shots. Okay, so you can kind of just play around with it, but there's many different options we could do. What if they were all 3-pointers? That would be 34 3-pointers and nothing else. What if they were all 2-pointers? That would be 51 2-pointers and nothing else. Okay, so there's a lot of different options you can choose here. Okay, and you need to at least have 5. What if we did, obviously just free throws? That would be a very extremely highly boring game. And finally, one more. Let's say we made 7 3-pointers. Okay. And let's say we made 15 free throws. Then we would have to make 33 2-pointers. Okay? So there's a few options. Yours can be different as long as they all add up to 102. Okay, number 3, use as many of the following shapes in any combinations as you need to try to fill in as much of the 12 by 12 grid as you can. You may rotate or reflect a shape if it helps. Write your answer showing how many of each shape you used. Okay, so basically, like if you wanted to use that A, you could just write A to show one right there. Okay, B, right? B. You could use E. Okay, so various different ways you could. D. And C finally. So you use all those and just see how many you get, and then tell us how many of each one you used. Okay, there's multiple different ways, so I'm not really going to show you one specific one on here. I think you guys are creative enough to do it on your own. Alright, graphing a linear equation and determining if a point is a solution. So a solution means it's a point on that line. So if we graph this equation, so we start at our y-intercept of -1, then 2 times x, so the slope of 2 over 1 means I go up 2 every time I go 1. We get a line that looks something like this. Obviously, I'm not always the most accurate at my points. Okay, so then the question is 3, 5 a solution? So if I go out 3, up 1, 2, 3, 4, 5, there's my point. Is it on the line? Yes, it is. So then it's a solution. So 3, 5 is a solution. Then I find some other points that would be solutions. 0, -1. Okay, would be another solution. -1, -3 would be another. Basically, any point on this line would be a solution for us. Okay, then y equals -3x plus 5. So we go up to 5, maybe. And so we're slope of -3, so -3 over 1. To the right 1. Oops, a little too far. So down 3, to the right 1. Or up 3, to the left 1. Okay, so there's my line. So again, I graph the point 3, 5. And it's definitely not a solution. But what would be 2 others? Well, I could go out 3, and then it'd be down -4. Or I could go back to -2, and it'd be +11. Okay? Or a multitude of other ones. Alright, so the tables represent different arithmetic sequences. Fill in the missing numbers, then write the explicit equation for each. So, we go from 17 to -7. So, looks like we're subtracting, okay, probably subtracting by 10, because that would, no, not by 10, to get to -7, so maybe subtract by 8. I think that's right? 17 minus 8 would be 9, then 1, then -7. Okay, so if we're going back to the 0 term, we would add 8, so we're minusing 8 each time. So that would be 25. So I go y equals my start number of 25. What am I doing? Subtracting 8. How many times? X amount of times. Okay, number 7. Oh, now we're going a lot further. Okay, but notice, if I would have went 17 minus negative 7 would have been a positive 24. We went once, twice, 3 times. So divide that by 3, we got 8. So, again, we're going the same distance, but this time it's going to take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if I divide by 12, I should subtract 2 each time. So, 15, 13, 11, 9, 7, 5, 3, 1, negative 1, negative 3, negative 5, then negative 7. So, yep, subtracting 2. Going backwards to the 0 term, it would be 19. So I'd get y equals 19 minus 2x. Okay, then this last one, we go 1, 2, 3, 4, 5, 6. 24 divided by 6 would give us 4. So subtract 4, give us 13, 9, 5, 1, negative 3. So going plus 4 would be 21 at the 0 term, so y equals 21 minus 4x. It says each of the sequences above begin and ends with the same number. Would the graph of each sequence represent the same line? No, because look, we technically, our y-intercept is different as well as our slope. So both y-intercepts and slopes are different. So they're not going to be the same. If you graphed each of these sequences and made them continuous by connecting each point, where would they intersect? Okay, so if we were to graph these, let's see what would we get. So we can see by graphing these, okay, the red line was 25 minus 8x, y-intercept of 25. We go down 8 to the right one, okay. Our green line was the next one, 19 minus 2x. So we start at 19 y-intercept, okay, and then we go down 2, or 4. Nope, it was 2. Then 21 minus 4, down 4 to the right one. So where they intersect, as we can see, is at this point 117. Why would they intersect right there? Well, because if we look at this, 117 is all the same on the table. The negative 7s all have different x values, so they wouldn't be the same. So definitely at 117. Okay? Alright, there we go, guys.